Okay, good afternoon, everybody. Let's continue with our journey here. So we'll go ahead and start talking about set and a few operations and a few things involving set. So first thing is union of two sets, A and B, their intersection, and then complement and the rule involving complements of set. And then we'll talk about other things involving sets. But let's go ahead and start off with this very simple example, okay? All right. So think of this example of rolling a die. Example, roll a die. If you roll a die, what do you get? Your outcomes, possible outcomes are either 1, 2, 3, 4, 5, or 6. And this is your sample space, right? Sample space. And remember, sample space is the collection of all simple events. And also remember that a simple event is an event that can happen only in one way, okay? A simple event is an event that can happen only in one way. And I'm going to define two sets. So let's define my first set A to be 2, 3, 5, 6. And my second set B to be 1, 4, 5, and 6. These are my two sets. Now, between these two sets, I'm going to create a few operations or what I call unions and intersections. Okay, so A union B. Okay, A union B is a set. Okay, so we define it to be a set of all elements X. Okay, such that X is an element of A or X is an element of B. Now, let me break it down this for you. What do I mean this? Okay. A union B, I create a new set from these two sets, this one and this one. This new set will have all the elements that belong either to A, okay, either to A or to B or to both of them. Okay. This new union, A union B, this new set includes all the items or all the things that either belongs to set A or it belongs to set B or both of them. If something repeats in both of them, we just write it once. So what is this set? What is such a set? If you go through these numbers in these sets, you will see that such a set is 1, 2, 3, 4, 5, and 6. If you go through these numbers, and these numbers, you'll see that these are the numbers. Even though 5 and 6 are common in both of them, okay? 5 and 6 are common in both of them, yet we write it only once here. So that's what it means to unite or make a union of two sets. Is this okay with everybody? Are you clear on this?
Yes.
Yep.
Next, I'm going to create intersection of two sets. Okay. A intersection B. Now, this is an upside down use. That's a symbol that we use for union. Now, what does that mean? It's the collection of all the sets such that X is an element of this little E is kind of like a Greek letter, epsilon type. is the indication that X belongs to this A and X belongs to, or X is an element of B. In this case, A intersection B is a set. A intersection B is a set. It contains all the items between A and B that are both in A and in B. That are both in A and in B. So that's what A intersection B means. So now let's look at the sets A and B and see which items are common or are in both of these sets, A and B. Which are those items? Which numbers are common in both A and B in the context of this example?
5 and 6.
5
5 and 6.
Exactly, 5 and 6. So that's A intersection B. Now, I kind of want to show you this thing, the difference between union and intersection. Look, in the case of union, we use or, and in the case of intersection, we use and. Or means one or the other, and in both. So here I kind of want to emphasize the or a little bit on the side. In the real world, let's say your mom says, hey, what do you want for Christmas? I want to give you either $100 or a dress. Okay? Or something equivalent of $100. So you either get $100 for Christmas or a gift worth $100, whatever your favorite gift is. In the real world, what we say is $100 or a gift. By that, we mean that you either get $100, but if you don't get $100, you're going to get the gift. That's what it means in the real world or. However, this or is slightly different. It's not exclusive or. This one is kind of like exclusive or one or the other. You can think of it that way. In this case, when I say or, means it could be in A, okay? It could be in A or in B or in both, okay? Both A and B. So kind of in a sense, you could think, okay, you can either get $100 or a gift or both. That kind of connotation that this or has. So it's important for you to realize that or has a slightly different meaning than what you are used to in your everyday use of or. And is the same, and because and means it's in A as well as in B. Now, next we are going to talk about a complement. A prime is used to indicate a complement. What is it? It's set of all the x's such that x does not belong to A. All right. Set of all x's such that x does not belong to A. That means x is not part of A. It's outside of A. A complement is outside of A. For example, you either come to class or you don't. So they're complementary events, right? You either graduate from college or you don't. If A is the event that you graduate from college, its complement is that you don't graduate from college. And complement of a set is very context dependent. That means depending on what we are talking about. I'm giving you very discrete examples to begin with so that you understand. Like if you toss a coin, event A is getting head, then complement of A is going to be getting tail. That means not getting head, right? So it's very simple. Now, in this context, what is a complement? And I want someone to kind of like help me here. What is not in A?
The numbers 1 and 4.
Exactly. The numbers 1 and 4, uno and cuatro, because 1 and 4 are not there. A complement is 1 or 4, 1 and 4. Okay, perfect. What about B complement or B prime? What is it? Lupi says 2 and 3. Let's see. Yes, you are correct. 2 and 3. Yeah. So you know how to find A complement. You know how to find B complement. In general, given the situation, given the experiment or trial, whatever you're doing, you should be able to find the complement of an event. Okay, if some event is defined in the context of an experiment or trial, you should be able to find the complement of that event. Complement is basically what is not there. So let me kind of give you an idea using something called Venn diagram. Okay, let's say this rectangle defines everything that's involved. So let's say this is your event A, then this circle contains event A. Then everything outside of this circle would be considered A complement or A prime. Sometimes people use A with a little c on the top too, but I tend to use A prime. In this case, A complement. Okay, so this circle represents event A. That means outside of this circle would represent A prime. Venn diagram. It's easier to see. Now, let me go ahead and talk about some interesting things about events A and B. Now, let's go ahead and talk about those. All right. So, what is the probability of event A? What is the probability of event A? So, what is the probability that event A will happen? What is it? What is the probability that event A will happen in the context of rolling a die?
One in six.
1 in 6, okay. How did you get that?
Well, thinking in terms of the die itself, it has 6 sides. So we have 1 in 6 chance of rolling the die and
Getting a number.
yeah.
But I'm talking about this event A. What is the probability that event A will happen?
4 out of 6 or 2/3.
2/3, who is talking?
Jessica.
Jessica, okay. George says 4 out of 6 too. Let me explain this to you, what I mean. When does event A happen? So let's take it to the side. A is the event that involves 2, 3, 5, and 6. A happens, or event A happens when one of these 4 numbers show up when you roll a die. If you roll a die, if one of these 4 numbers show up, then A happens, right? So if you roll a die, 2 shows up, then A has happened. If you roll a die, 3 shows up, then A has happened. If you roll a die, 5 showed up, then A happens. If you roll a die, 6 shows up, then A has happened. Okay? You can have only one outcome when you roll a die. So if the outcome happens to be one of these 4, then event A has happened. What if you roll a die and 4 shows up? Did event A happen? You roll a die, the outcome is 4. Did event A happen or no?
No.
The answer is no, it hasn't happened. So the probability of event A is 4 out of the total 6 possible ways. So that is 2 out of 3 or 2/3, which is approximately 67%. Similarly, probability of event B, by the way, is what? Look at event B right here. So probability of event B is 4 out of 6 or 2/3 or approximately 67%. That's what it means, event A and B happening and the associated probability. All right. Now I'm going to do probability of A union B. Now I know A union B is this, right? 1, 2, 3, 4, 5, 6. I found it, which is the same as finding the probability of 1, 2, 3, 4, 5, or 6. And what is that probability? Probability of A union B is what? Luis Morales, what is the probability of A union B? Luis Morales. Anybody else wants to try? What is the probability of A union B?
1 or 100%.
1 or 100%, exactly. Look, A union B is nothing but 1 through 6. So if you roll a die, your outcome has to be one of these 6 values, 1 through 6, right? 1 through 6. So event A union B will for sure happen if you roll a die. And look, there are 6 of them here, 6 out of 6, or 1 or 100%. So there's a 100% chance that A union B will happen. Now let's go ahead and talk about A intersection B, which is the same as saying probability of, and we found it, 5, 6. This one, A intersection B, is right here. So probability of A intersection B is 5, 6. Then there's going to be 2 out of 6 because there are 2 items, 5 and 6 are 2 numbers, which is 1/3 or approximately 33% chance. A intersection B. Now, what is the probability of A complement? A complement, which is also easy. We found it. A complement is 1 and 4. That's 2 out of 6 is 1/3. Similarly, what is the probability of B complement, which is also 2 out of 6? That is 1/3. So these things should be pretty clear to you, right? Very simple how to take unions of 2 sets and how to take intersection or find complement of 2 sets, complement of sets, etc. Now, having defined this, I want to find something else. So let's say A prime union B prime. We have found A prime and B prime. Union of A prime and B prime would be what? Union of this with this. And that would be what? What value would that be, everyone? It is 1, 2, 3, and 4. A prime union B prime, or A complement union with B complement, because for A complement has 1 and 4, B complement has 2 and 3. So if you combine them, you get 1, 2, 3, and 4. So now what is the probability of A complement union B complement, which is the same as finding the probability of this, so which is 4 out of 6, right? That is 2/3. Simple. Now let me define something slightly different. A intersection B, okay? A intersection B, in our case, is 5 and 6, right? 5, 6. But let's define two other sets. C is equal to 3, 6, and D is equal to 1 and 2, 1, 2. What is C intersection D? In this case, C intersection D, what would that be? Adeline Lopez, what do you think? C intersection D here. Adeline Lopez, are you there?
I don't know how to explain it, but I'm trying to explain it, but I'm not sure how.
Try. See, what is it? Just tell me in ordinary language. Don't worry about the math part. What are you trying to do here? How do you find C intersection D?
I don't know how to explain it.
You don't know how to explain it. Okay. First of all, intersection means what? We are looking for items such that the item is in set C as well as in set D, right? The item is in set C as well as in set D. That means in both of them. Is there anything there that is in both of them?
No.
So that means there is nothing, right? So that means it is empty set. Sometimes empty set is denoted by this, but more commonly empty set is denoted by phi, Greek letter. So that's PHI, phi, the Greek letter phi. So the intersection of two sets, if they are empty, is called that they are mutually exclusive. Mutually exclusive. Or also we call them, or also call them disjoint. So from now on, if you hear the terms mutually exclusive or disjoint, you should right away think, oh, okay, that's what they mean. That means there is nothing common. All right. There is nothing common between these two things. These two things are mutually exclusive. Sometimes people use that expression. That means there is nothing common between them. They're separate. Now, remember, probability of C intersection D is the same as the probability of the empty set. What is the probability of the empty set from the characteristic of probability function? What is the probability of empty set? By definition, the probability of the empty set is what? 0. The probability of the empty set is 0. So there are a couple of ways you can say that two events are disjoint if their intersection, C and D, their intersection is empty set, they're disjoint, or sometimes it might be easier to show that probability of C intersection D is 0. Okay, that's also something that you could use. If their probabilities are 0 intersection, then those two sets are what? disjoint. If you have two sets whose probability is 0, intersection of those two sets, then the sets are mutually exclusive or disjoint. So that's what it is. On the other hand, A intersection B, by the way, A intersection B is not disjoint because it has something in them. A intersection B is 5 and 6. So probability of A intersection B is 2 out of 6 or 1/3, which is not equal to 0, right? Therefore, A and B are not mutually exclusive or disjoint. A and B are not mutually exclusive or disjoint. That's what it is, all right? Now, are you okay with these things? With this definition of set and definition of events and how an event happens, under what circumstances, when it does not happen. Like event B is gonna happen. If you roll a die, you get either 1 or 4 or 5 or 6. Okay, event A is gonna happen. If you roll a die, you get 2, 3, 5, or 6. You cannot get all of them together or even more than one together. One of those 4 you'll get, because if you roll a die, your outcome is only one event. If that event happens to be one of the 4 events here in A, then A has happened. If that event happens to be one of the 4 events in B, the event B has happened. So that's what I mean. Okay, any question, anybody, about this, all of this? A lot of information here, but not too complex. Once you follow the chain of thoughts, it kind of naturally follows. Any question, anybody, about all of this? Okay, if not, let's go to the next. Let's look at the slide. So here in this slide, I covered this union of two sets, intersection of two sets, complement of two sets, and the complement rule. Maybe I should talk about it. I forgot to mention that. We know event A and we know event A prime, or complement of A. Probability that an event A will happen plus the probability that an event A will not happen. Not happen means a complement must always add up to 1. Something can either happen or it cannot happen. There is nothing in between. So the probability of event A plus the probability of A prime is equal to 1. The probability of event A plus the probability of A prime is equal to 1 or 100%. And from this, we have derived in the last class that probability of at least one of something, at least one of something that you are considering is equal to 1 minus the probability of none. Or equivalently, by rearranging the terms, we could write probability of none is equal to 1 minus the probability of at least 1. Now, depending on what you are looking for, if you're looking for some event where you're looking for at least one of something happens, then you may use this version. But on the other hand, if you're looking for that none of that event has happened, then you may be using this version. It's the same thing. It comes from this probability of A plus probability of A complement. Remember, event A, if event A is at least one of something, at least one of something, right? At least you have one apple, let's say, then A complement is going to be you have no apples or none. So we know that probability, let me use a brighter color. We know that probability of A plus probability of A prime is equal to 1, but instead of A, if we write at least one, so we have probability of at least one plus the probability of A prime none, probability of none is equal to 1. Because at least one and none, they are complement of each other. That's why using the complement rule, you can go ahead and find at least one of something or none of something. So that is what the complement rule is. Next, anything on this topic, anybody? All right. Next, we are going to talk about sort of disjoint. We talked about it. Two events are disjoint. Let's talk about union. Okay. We have defined what is A union B. Now I'm gonna tell you what does it mean to find the probability of A union B. This is kind of like a formula you can think of, and we are gonna be using it. Probability of A union B. What it is, that probability of A plus probability of B minus the probability of A union B. Probability of A plus probability of B minus the probability of A union B. Now you might be asking me, where did you get that formula? Suddenly you gave me this formula. Where does it come from? Now let me actually give you an example so that you can see it. Think of this is your universe of things when you are talking about some experiment or trial. So let's say this area represents, so all of it represents 100% or one rectangle. Okay. So this is event A, or probability of event A, I'd say. And this other circle area represents probability of event B. Okay. So area A and area B, left circle, probability of A, right circle, probability of B. Okay. A union B, when you unite these two sets, okay, then what you get is the intersection plus individual areas, right? Now, look, if you think of A union B, then it would be all the areas. So let me use a different color slightly. You're looking for this area, okay? But note that this middle region is calculated twice. Once with A, right? Once with probability of A and once with probability of B. So since it is being calculated twice, you subtract it once. So when I say P of A, that means the left circle. P of B, that means the right circle, okay? Then A intersection B, which means this one, right? This middle portion, A intersect. Oh, I made a mistake, sorry. This is not supposed to be union. That's why I'm kind of thinking, hey, you, go away. Okay. Sorry. A intersection B. What happened? Okay, let me just take it out. All right. I meant A intersection B. Sorry about that. So this intersection part, this shaded part, we are calculating it twice, this shaded region, once with A, another times with B. So probability of A union B is probability of A plus probability of B minus probability of A intersection B. Another way, just instead of P of A, if we are dealing with two sets, just think of two sets A and B. A and B. These are two sets. And this is the overlapped portion. This is the overlapped portion. This is common in A and in B. So if we want to find a probability of A union B, okay, A union B, then look, if you do probability of A plus probability of B, okay, then this portion, this shaded region, is being calculated twice. So you just have to subtract once. Probability of A intersection B, probability of A intersection B.
Can you do an example?
I will do many of them. Okay, probability of A intersection B. So remember that rule. Probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B, because you are calculating the shaded region twice. That's why you have to subtract. However, if you're dealing with two sets where they do not overlap, let's say A and B, okay? So there is some probability function that you associate with set A, some probability function that you associate with set B. Here, you don't have to worry about this because this is going to be 0, because for these two particular sets, A intersection B is nothing but the empty set, right? A intersection B is nothing but the empty set. So probability of the empty set is 0. So is everybody okay with probability of A union B is probability of A plus probability of B minus the probability of A intersection B? Is it at least somewhat okay, everyone?
Yeah, I somewhat understand.
Okay, just remember this and this diagram. That kind of is Venn diagram, and it kind of gives you an idea, a visual way of thinking about it. That gives you a better understanding. Now let's talk about some examples, as Don, you were asking. So let's jump into the examples. Okay. Some examples here. I'm going. So now, one student said, I'm getting cut off once in a while. Are you guys having difficulties hearing me? Anybody?
No,
No,
I don't have any problem.
I don't have any problems.
Okay. Nayeli, probably your internet, okay? Looks like it may be your case. So check, I don't know. I know it's a generic and an answer that you don't want to hear. Check your internet. There's nothing you can do really because you're not the person in control of the internet, is the provider. If you cannot hear me, just log out and try to log back in. That might help. Next, let's go ahead and do some examples here. All right. Your chances of passing statistics is 80%, okay? Your chances of passing statistics is 80%. And your chances of passing chemistry or organic chemistry is 70%. The probability that you pass both the classes is 55%. Answer the following questions based on the above information. Now, if you look at these percentages, you can see that they add up to more than 100%. Like, look, 80% plus 70%, 70% plus, I can't write over here, plus 55%. Obviously is greater than 100%. Probability, sum of all the probabilities must be 1. Sum of all the probabilities must be 1 or 100%. Okay, remember, probability of the sample space is 1. Now it is over 100%. Is there a problem? The answer is no. Why is it not a problem? Because there is overlapping probability here. There is overlapping probabilities. Overlapping probabilities. All right. Now, create a Venn diagram for the scenario. So you have two events. Event A, so let's define these events as S is an event okay? And C is another event. S is the event that you pass statistics. C is the event that you pass chemistry. So remember what these events mean. S is the event that you pass statistics. C is the event that you pass chemistry. So let's say this circle represents the probability that you pass statistics. Let me take the background off so that at least you can see things clearly. And C is the event that you pass chemistry. Or in this case, probability of S is represented by this big circle, a left circle. Probability of C is represented by this right circle. Now there is an overlapping probability, which is 55% chance that you pass both statistics and chemistry. You pass both statistics and chemistry. And they also tell you that the chance of you passing statistics is, I think it's 85%, is it? No, 80%. 80% chances of you passing chemistry is 70%. So left circle, right circle. Now middle or the overlapping region between these two circles is 55%. And let's put a big square around it to show that it's everything that could happen in the universe or in the world of taking two classes statistics. So all the probabilities. Of course, the diagram is not proportional, it's a sketch. So now, based on this, we want to answer a bunch of questions. So first question, so Venn diagram, we kind of have drawn it. Find the probability that there is no A. You just pass stats. Find the probability that you only pass stats. So I should probably say probability that a student only passes stats, okay? Find the probability that a student passes stats only, all right? Now let's go back. So what does that mean? You pass stats. By looking at this diagram, can you identify the region? Identify the region that would indicate that you only pass statistics. And if you can find that area, that will represent the probability of passing statistics only. So we are looking for probability. So let me write here. We are looking for probability of S. S is the event that you pass statistics only. Okay. This S, I have to be a little bit careful here. I'm going to write it out. S is the event that you pass stats, okay? But you can pass stats as well as you can pass chemistry too. So let me just clarify it here. I'm looking for the probability that you pass stats only. So let's make sure that we are clear on this. Find the probability that you pass stats only. Okay, somebody has something in the chat. What is it? Somebody says 80% and somebody says 25%. George says 80% and then Lupi says, sorry, George says 25%, Lupi says 80%. Who should I believe? A third person. Who should I believe? Lysandra?
Yes.
Who should I believe? And why?
Could you ask that question again? My internet was going on and off.
Oh, okay. Find the probability that a student passes statistics only. A student passes statistics only. Pedro, what do you think?
Is
Pedro,
it 80%?
80%. Okay. Anybody else? Any other volunteer? Alondra, what do you think? Alondra, what is?
I think it's 80% or 80.
All right, I'd have to probably go with George then. It's 25%. Look, you pass statistics only. That means we are talking about this region. If you're in the middle, you not only pass statistics, but also pass what? Chemistry. That's not what we are interested in. I said, that's why I kind of clarified it here. Probability that statistics only. So that would be 80% minus 55%. 80% chance that you will pass statistics, then 55% chance that out of this 80%, 55% will also pass chemistry. But we don't want those group. Okay? So 85 take away 55 is 25%. So 25% or 0.25 chance that a student passes statistics only. The next question, I'm gonna write it here even without writing, looking, probability that a student passes chemistry only. Now this should be easy now. Chemistry only, we are talking about which region? Just this region. Remember, the areas are not proportional. So how do I find the right shaded region? That would be what number?
So you would subtract 70 minus 55, which would give you 15?
Exactly, 70% minus 55%, that's gonna give you 15% or 0.15. Now, what is the probability that a student passes statistics and chemistry? And chemistry, which is pretty easy, that's given in the problem, or 55% or 0.55. All right. Next, what is the probability that a student passes at least one of the classes? One of the classes. The student passes at least one of the classes. So this one is a little bit tricky. At least one of the classes. At least one of the classes means what? It either the student either passes chemistry or statistics or both. At least one means one or more. Remember, we said at least one means at least one means one or more. That's what it means. At least one means one or more. So we need to find out what is the probability that a student passes statistics, what is the probability that a student passes chemistry, plus what's the probability that a student passes both statistics and chemistry. Can you walk me through the process, anybody?
Would you add the statistics and the other class, 80 and 70, and subtract 55?
No. Yes, you could do it that way. Yes. Yeah.
Then it would be 95% chance.
Yes, absolutely. You could do it 80% plus 70% minus 55%, right? Which is gonna be 95%. That's one way of doing it. But another way of doing the same thing would be take this 25%, 15%, and this is 0.15, right? So 0.25 plus 0.55 plus 0.15 is gonna give you 0.95 or the same as 95%. Now this one, who gave me this answer, by the way?
Danny.
Danny, what you did, you actually used A union B, okay? So, what did I say? Probability of A union B, that's what you used. So let me. You actually did probability of A union B, which is the probability of A plus probability of B minus the probability of A intersection B. Probability of A is 70%. Probability that a student passes statistics, or in this case, I'm going to actually write it with S and C. That way is more clear. Probability of S union C. S is the event that you pass statistics. C is the event that you pass chemistry. Is the same as probability of S plus probability of C minus the probability of S intersection C, right? Now, let's go up instead of going down. Probability of S is pass statistics, 80% chance, or 0.8, plus probability of C, pass chemistry, 70% chance, 0.7, minus the probability that a student passes both, which is 55% or 0.55, that is 1.5 minus 0.55, which is nothing but 0.95, which is the same as 95%. So this is what I would like you to think about. That's why I gave you this problem. Don, you are asking about example, right? So this is the example.
Yeah, that was a good example. Thank you.
So probability of S union C is probability of S plus probability of C minus the probability of the intersection. Because this middle portion, you counted it twice, once with this, once with that, and together you count it twice, so you subtract once, which is what you do here. All right, the last question, probability at least one of the classes. Find the probability that a student passes no classes. Or probability of none. Remember, probability of none is 1 minus the probability of at least 1. I just talked about it. Probability of none is 1 minus the probability of at least 1, which is this. 1 minus probability of at least 1, we found 95% or 0.95, which is 0.05. That, by the way, is 5%. There is a 5% chance that a student will pass none of these classes. And that is, by the way, a complete example, okay? That is a complete example of using this, what we call sometimes addition rule for probability, okay? Probability of A union B is probability of A plus probability of B minus the probability of A intersection B. That's the addition rule. Okay, that's what it is. Now, having said that, let's go ahead and do the next problem. Any question before I move on from this question? By the way, if I bring in if you can read it, let's clean it up. All these questions in this slide, I answered all of them, okay?
Did you answer what is the probability that you pass only one class?
Oh, did I not? Probability that you, okay. Probability that you pass only one class, or a student passes only one class. You already know how to do that, but let's go ahead and do it. You pass only one class. That means what? You either pass statistics or you pass what? You either pass statistics or you pass chemistry. So you pass statistics only, So S only plus probability of C only, which is S only is 0.25 plus C only is 0.15, which is 0.40. That is 40% chance that you pass one class or the other. Okay. Any question, anybody on this? No question? Everybody okay? All
So-
right. Yeah, go ahead.
No, so far so good. Thanks.
So far, so good. All good. Okay, Pedro. Now let's go ahead and see. I'm thinking I meant to say one last thing on this, but I forgot what it is. Let me see. Let me look at the slide. If there is anything I meant to say. No, I don't see anything. So let's go ahead and do the next problem. Again, is the exact same problem, duplicate, but this time we are talking about coffee drinkers and tea drinkers. 85% of the people in the society drink coffee, 40% of the people drink tea, 35% drink both coffee and tea. Based on this information, answer the following questions. Exact same problem. Exactly same problem. I want you to create a diagram on this, everyone, okay? I want you to create a diagram and then answer all of these questions and write it. Everybody, I want you to write it. And I'm gonna randomly select a few people, not one. You either send the response to me or you show it to me. That's why I kind of want you to write big, okay? Write big so that you can unlock your video and show it on the screen so that we can read it. And I will ask people to send it to me as well. So the reason for doing this is to ensure that you actually are doing work on the other side of the Zoom meeting, because I can't see. All right, if you are in a physical class, I'd be seeing at least externally what you're doing, or I could go and check your work. So let's go ahead and give you like 5 minutes. I'll give you 5 minutes and work on it, and then we will go ahead and talk about this problem. All right, so let's start. All right, so let's go ahead and work on this problem exactly the same way that we did the last one. So we have the following scenario. We have tea drinker and coffee drinkers. So let's say this is your coffee drinkers, 85%. And there's an overlap also. This is your tea drinkers, that's 40%. And there's an overlap of 35%. 35%. And this is everything all together. So I'm gonna go ahead and take the background off. Let's define two events. T is the event that somebody drinks tea. C is the event that somebody drinks coffee, okay? So coffee, tea. So now, let me go ahead. Is there a problem adding over 100% all the percentages? The answer is no, because there is overlap. There is overlapping probabilities, so it's okay. The Venn diagram is this. Now, find the probability that somebody drinks coffee only. So let's do one by one. Let's say 1. Probability that somebody drinks coffee only, not just coffee, but coffee only. And that, by the way, would be this region. And that would be what percent? 85% chance that somebody drinks coffee, 35% chance that somebody out of those people, 35% chance that a group would drink coffee and tea both. So 85% minus 35% is 50% or 0.5. Okay, so coffee only is 50%. Number 2, probability that somebody drinks tea only. Again, that would be this portion. So 40% minus 35% is 5% or 0.05 or 0.05, which is 5%. Let me clarify something here. Students sometimes make mistake. They mean to say 5%, but they write 0.5, which is 50%. 0.5 is actually 50%, but 5% is 0.05. So please note of that thing. I have seen many times students, they make this mistake. They say, they mean to say 5%, but they write 0.5, which is 50%. So the next, number 3, probability that a randomly selected person drinks coffee only or tea only. And that would be just the black shaded region on both sides. So that would be 50% or 0.5 plus 0.05. That is going to give you 0.55 or 55% chance. There is a 55% chance that somebody drinks only coffee or only tea. Number 4, what is the probability that somebody drinks both, which is given? Probability of drinking both. Tea and coffee is 35% or 0.35. Number 5, what is the probability? What is number 5? Drink at least one of the drinks. Probability of drinking at least one of the drinks. Which, by the way, turns out that you are looking for probability of C union T. Okay, C union T, which is the probability of C plus probability of T minus the probability of C intersection T. Probability that a person drinks coffee is 85% or 0.85, plus probability that a person drinks tea is 40% or 0.40, minus the probability that a person drinks both coffee and tea is 0.35 or 35%. So what does it come out to? 85, 125, 1.25 minus 0.35, that gives you 0.90 or 90% chance. There is a 90% chance that a person drinks at least one of the drinks. Number 6, what is the probability that a person does not drink any of these drinks? None, which is probability of none is 1 minus the probability of at least 1, right? And we found it. 1 minus the at least 1 is 0.9, which is 0.1, or there is a 10% chance that a person drinks none of these drinks. All right. Okay. Now let's go ahead and do something else. That answers all of the questions, but there is something that I told you I forgot. Now it came to my mind. C, so let's say our events are C and T, right? Okay, so you can pass chemistry. So what could happen? Okay, what could happen in this world of tea and coffee? I went back to chemistry for a second, see for chemistry. Tea and coffee. You can drink coffee and you can drink tea. Okay, that could happen. You can drink coffee, but you don't drink tea. Let's denote it by T prime. Or you could not drink coffee, C prime, but drink tea. Or you could drink not coffee, not tea. That means you drink neither. These are the things that could happen. So in your case, in this scenario, your sample space is going to be this, basically. Drinking both tea and coffee, okay? Drinking both tea and coffee, drinking only coffee, not tea, drinking only tea, not coffee, or drinking none of these drinks. So if you break it down into simple events, okay? So let's say I break it down into collection of simple events. So C and T, that means you drink coffee and tea, both. C and T prime, that means you drink coffee but not tea. Or C prime T, that means you drink tea but not coffee. C prime T prime, meaning you don't drink neither coffee nor tea. So these are all the things that could happen. So in the diagram, if you don't belong to these circles, if you don't belong to any of these circles, you must belong to the outside of this rectangle. And that outside is 10%, by the way. 10% chance that you do not drink either of these tea, either of these drinks, tea or coffee. So outside of these circles is the group of people that do not drink either tea or coffee. Any question? Anybody? Don, is it clear now?
Yeah, it seems okay.
Seems okay. All right. So let's clean it up. Go back to our screen. We talked about disjoint events. Okay. Here, I kind of did this problem, but let me go ahead and do it again. All right. Just to give you a sense of what I'm talking about. So let's go ahead and work on it. In the context of rolling a die, I define two events: A, 2, 4, 5, 6, 2, 4, 5, and 6. And event B is 1, 3, 4, 5. 1, 3, 4, 5. Event A and event B. Now, event A, is it a simple event or compound event? And are the events disjoint? And then find the probabilities A, B, A union B, intersection B, A prime B, as probability of A prime, probability of B prime, and probability of A prime union B prime. So, okay, good. Now, let's go ahead and hide these things. So let's do one by one. Is A simple event? Same for B. So let's answer the first question. Is A simple event? If yes, explain. If no, explain.
Yes, it's a simple event because if it was compound, it would happen twice.
Okay.
Simple events
right.
can happen once.
What is a simple event? An event that can happen only in one way, correct?
Correct.
So can A happen only in one way?
Wouldn't that be yes?
Yeah, what is it?
Yes.
Yes, okay. For some reason, I kind of think of it differently. When can A happen? Just think of that event. When can A happen?
Is it a compound because it could happen at 2, 4, 5, and 6?
See, A can happen if you roll a die if two shows up, right? If you roll a die, if 4 shows up, A can also happen, right? So it can happen in more than one way. As a matter of fact, it happens in 4 different ways, right? Event A can happen if 2 shows up, or 4 shows up, or 5 shows up, or 6 shows up. So that's kind of like 4 different ways of this event happening. So I don't call it a simple event. It's a compound event or not a simple event. Is the idea clear to everybody? It's a compound event or not a simple event. Same for B. B can happen if 1 shows up, 3 shows up, 4 shows up, and 5 shows up. So it could happen 1, 2, 3, and 4 different ways. Therefore, B is not a simple event. The answer is no. Are the events disjoint? Meaning probability of A intersection B, that's one way of doing it. Probability of A intersection B is equal to 0, or A intersection B is the empty set. So this is something you should be able to do. What is A intersection B? That means what are the items that are common both in A and in B, which is what?
4 and 5?
4 and 5. So obviously this is not an empty set. Therefore, not disjoint. Or mutually exclusive. It's not disjoint or it is mutually exclusive. It's not disjoint or it's mutually exclusive. Is it clear, everyone?
Yes.
Yes.
But also remember, probability of A intersection B is the same as the probability of 4 and 5, right? Which is the same as 2 out of 6, or 1/3. Obviously, it is not 0, right? So these are 2 different ways of showing that 2 events are disjoint. So this and this, these are 2 different ways of showing that 2 events are not disjoint or disjoint, whatever your objective is. Now, probability of A union B. So let's find out A union B. So number 3. No, first find out probability of A, which we did. There are 4 items in this set. So it's 4 out of 6, or 2/3. Number 4, probability of B. Again, the same thing. 4 out of 6, 2/3. Number 5, probability of A union B. So first find out what is A union B. If you union them, you're gonna find 1, 2, 3, 4, 5, 6. So probability of A union B is the probability of this entire set, right? Which is basically the sample space for rolling a die. So that should be, if you roll a die, it has to be one of these 6 numbers. So it's 6 out of 6, or 1, or 100% probability of A union B. Number 6, probability of A intersection B, which you already did. A intersection B is 1/3, which is right here. A intersection B. Number 7, probability of A complement. What is A complement here? That means we are looking for items that are not in A. A complement means we are looking for items that are not in A. What is it?
Three.
3. Is that all?
1.
1 and 3. 1 and 3. So the probability of A prime is 2 out of 6 or 1/3. Number 8. Probability of B prime we are looking for, but what is B prime first? B prime is 2 and 6. So probability B prime is 2 out of 6 or 1/3. What is the probability of A prime union B prime? So A prime union B prime. So look at B prime, look at A prime. If you unite them or create a union of them, you get 1, 2, 3, and 6. And probability of A prime or A complement union B complement is 4 out of 6 or 2/3. What is the probability of A complement? So let's actually do this first. That was number 9. Then number 10. Number 10, A complement intersection with B complement. What is that? What is A complement intersection B complement? A complement intersection B complement. What is it? Alicia, what is A complement intersection B complement? Alicia? Dennis Lopez, what is A complement intersection B complement?
Let me check. Wouldn't it be the YG?
First off, find out A complement is this, right? And B complement is this. So between these two sets, what is common? Is there
I know
anything
that.
common between them?
No.
No, so that's the empty set, right? That means
Yeah.
nothing. So the probability of the empty set by definition is 0. A intersection, I prime intersection B prime is the probability of the empty set, which is 0. That means these two events are disjoint. A prime and B prime are disjoint. /ME, mutually exclusive. Okay, did I miss anything for this example? I don't think I did. Let me check. Compound, simple, events disjoint, A prime, B prime, A union B, A B, A union. I even did one extra, which is not here. A prime intersection B prime. So good. It's all good. This one is done. This slide. So next slide is slide number 72, conditional probability. Conditional probability is a very powerful thing nowadays. It has a lot of application in the real world. You may not think about it, but it is actually true. Conditional probability is very useful. So let's go ahead and use the red color so that you can see it clearly. Conditional probability, the probability of an event given that some other event has already happened and is denoted by P of A with a bar and next to it B. Whatever is to the right of that vertical bar, those events are given. That means that has already happened. Something is given means it has already happened. You can assume that it has happened. So, conditional probability. So my favorite example is the NBA. So let's say I want to find out the probability that a person plays in the NBA. That chance, by the way, is pretty small. It's 1 out of, I think, 500,000, 500, 1, 2, 3. 1 out of 500,000, okay? 1 out of 500,000. How did I come up with this number? There are about 500 people playing in the NBA, okay? Roughly about close to 500 people playing in the NBA, and we have about roughly 250 million people. It's actually 270, but 250 million. So that comes out to be, in the general population, about 1 in 500,000 people are playing in the NBA. Let me just double check my number. 250 million divided by 500. Yep. 1 in 500,000. So your chances of playing in NBA is 1 in 500,000. That's probably not correct, okay? This probability cannot be, if you think of things a bit more subtly, it's not true. That chance is probably less. If somebody is, let's say, 5 feet 6 inches, the probability of playing in the NBA is not 1 in 500,000. It's probability is almost 0, or very close to 0, because of the height disadvantage, right? Now, let's say your chances of playing in the NBA is 1 in 500,000 people. But if I give you the additional information that your probability of playing in the NBA, given that this vertical line indicates that given that you are, or the person you are considering is over 6 feet 6 inches tall, the probability of playing in the NBA, given that the person under consideration is over 6.5 feet tall, then this probability definitely goes up significantly compared to 1 in 500,000. Okay, so there are real world scenarios where a lot of situations happen where if you are given something, then the probability of something else happening goes up significantly. Here is an example. If you go to the doctor, a very common thing that they ask you, some family history, did your parents have cancer, or is there cancer in your family? Is there heart attack in your family? Or was there any heart attack in your family? Or is there anybody, or was there anybody who suffered from diabetes in your family? Why do they ask you these questions? Do you think that they just want to collect data about you? And these are technically somewhat private information you don't want to share with others. This is your personal health information or family health information, yet you share it with the doctor. Why? Because let's say you're a person who goes to the doctor with certain symptoms, and you're obese and you have a family history of heart disease, then what is the probability? So that what the doctor is doing is, in essence, what is the probability of you having some sort of cardiac issues, given that you have a family history of heart problem? What is the probability that you will have some sort of cardiac issue? It could be chances of having a heart attack, chances of having heart problems, or clot, whatever they call. Given that you have a family history of heart disease, what are the chances of you having some sort of cardiac issue? Do you see? This given is very useful. Now, if a random person goes, the doctor might be, he or she might be thinking, oh, is this a heart problem or is it something else? Looking at the symptoms, he or she might be confused. But if he or she has the information that you have a history of this, then you may have this. So doctor is not actually sitting down with a calculator or some program and doing the calculation to find out that whether you have cardiac problems or not. But actually, on a second thought, they do. The last time I did my physical, my doctor said, given my age, given my ethnicity, given my dietary habit, I have within the next 10, 15 years, I have about 5% chance of having heart attack. Okay, which could happen, right? So he actually put in all this information in a program. So they do these conditional probabilities. So the point here is this. What is the probability of some event given that some other event has happened? What is the probability of you having pre-diabetes given that you have a family history of diabetes? Okay. What is the probability that you have diabetes given your ethnicity? Because in Asian countries, we tend to eat a lot of rice, which is carb that could lead potentially to diabetes. As a matter of fact, it is a fact that a higher percentage of people from Asian countries, particularly Southeast Asian, they suffer from diabetes because of their dietary habits. What is the probability of you having flu? Probability of flu is much less than probability of flu given that is the cold season. Do you see how it changes? So this is called conditional probability. All right. And the most interesting one I have seen, one time I went to a doctor and somehow this conversation came along, probability of cancer. It depends on a few things, religion, gender, and location. What I was told, I'm not really thorough on this information, but I'm pretty sure it exists. Probability of having certain type of cancer, not all cancer, certain type of cancer is higher given that the person is Jewish and it's a female and comes from some location in the Eastern European region. Okay. So that person has a higher chance of having that particular type of cancer if the person is Jewish, female Jewish, female, and comes from certain region of the Eastern Europe. I thought that was kind of very interesting. How does that happen? That apparently it does. I know for sure ethnicity makes a difference, right? Certain disease. Or maybe another very interesting thing that skin cancer is another example. If you live in, I think, North America, if you have lighter skin, you are probably more prone to having skin cancer compared to if you have darker skin. Skin cancer is not so common in Asian countries, or at least where I come from, Southeast Asian country. But in the US, it's probably more common. So you got the idea of conditional probability. So now I'm kind of going to stop here. Next time, what I'm going to talk about is this, how to use the definition of conditional probability of A given B, okay? How we use it in defining A and B, two events. What does it mean to find the probability of A and B, okay? And we will start off here and we will go from there. And then after that, we will do some conditional probability problems. And then we'll talk about also independence, because conditional probability and independence, they kind of go in together. And once we do that, we are going to go into Bayes' theorem, which is another example of conditional probability. Bayes' theorem is very important. Like one good example could be like your Gmail, okay, Google Mail. It has different categories. I hope you don't think that somebody is separating the emails from you, for you. Every time an email comes in, They put it in either inbox or social or promotions. They categorize them. They use conditional probability. They look at an email and look for certain things. So what is the probability? Here is an example you can think. What is the probability that hold on a second. Okay. What is the probability that an email is a spam given that it has the word buy, okay, buy now or something, right? Or it has the word sale, it has the word promotion. Do you see? Conditional probability. So Google has very sophisticated sorting system using conditional probability and machine learning / artificial intelligence that allows them to instantaneously kind of classify these emails as they come in, okay, based on the content, based on many factors. They take into consideration many factors, but I just gave you some simple examples, okay, based on these words, presence of these words, would you consider it a spam? And they associate a probability. Okay, if there's a 70% chance that it's a spam, they're going to put it in the spam category or social category or whatever category they have, as opposed to putting it in the inbox as an important email. So you can see the conditional probability is very important. They don't do it manually. If they were to do it manually, they probably will not be in business because billions of emails are going back and forth, right? So it's done automatically, almost instantaneously through some sort of machine learning algorithm that uses conditional probability. All right, that's all for the day. Thank you so very much. You guys have a wonderful weekend. There is a homework due. There is a homework on probability, but I don't think I have covered everything that you need to know in order to do the entire homework. So do as much as you can, but if there is something involving conditional probability, and I'm very sure there is at least one problem there involving conditional probability, that one you don't have to do yet. You can try it, look at the lecture notes, look at the course materials and try doing it. And then if you can do it, fine. If not, I'll go over this on Monday. All right. In between, you guys have a wonderful evening, rest of the week and weekend. Stay safe, stay healthy, and we'll talk on Monday. Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.